Should I wait for some more people to join or shall we start? Can you see my screen? Hello, Urja. Great. Okay, then we'll proceed. Right, I welcome you all to the 10th week of live interaction session for the course Principles of Downstream Techniques in Bioprocess. Let's start. So, the topic of the week is continuing with chromatography. The first question is starter question, very simple. Please use the chat box. Drop in your options. If the concentration of the salt in the mobile phase is constant with time, then it is called A. Isocratic illusion, B. Stepwise illusion, C. Gradient illusion, and D. Affinity illusion. So we are talking in terms of chromatography, where you have a stationary and mobile phase. So the mobile phase is the one which is going to help you load as well as elute the components. So during this process of elution, the mobile phase can change or not change in terms of its composition. So if its composition, right now we're talking about the salt concentration, if it is constant with time, what do you call it? I mean, of course, you have heard these words, right? Isobaric, isotherm, isocratic. Does it ring any bells? Hmm, isomer, is that the right spelling? It's been a long time since I wrote isosceles triangle. But at least it should give you a hint, right? When something is constant, isotropy, isotropic, right? So in stepwise solution illusion as well as gradient illusion, you're going to have the mobile phase concentration changing in steps, or it is going to continuously vary over time, either increase or decrease in salt solution, right? With respect to time, the concentration is going to either increase or decrease, correct? If it is not going to continuously do but do it rather in steps, it is called stepwise illusion. Affinity illusion is a bogus option here. The isocratic is the right one. Okay. So question 2. Which of the following conditions is of reverse phase chromatography? Option A. The mobile phase is non-polar and stationary phase is polar. The mobile phase is polar and stationary phase is non-polar, just the opposite. Then both the mobile phase and the stationary phase are organic, and both mobile phase and stationary phase are inorganic. So what is it? Generally, what do you have? So what is a normal phase chromatography? I mean, you don't really call them normal phase, but I'm just hinting so that what is generally observed and that is reversed in some sense, and that's why you called it reverse phase chromatography, right? Any option, at least attempt. It doesn't matter if it's wrong. Thank you, Urja. So, any disagreements or any seconding of Urja's option? So, in reversed phase chromatography, the mobile phase is going to be polar or non-polar. Do you all listen to the lectures or not? Okay. In general, the stationary phase, uh, you have polar stationary phase and non-polar mobile phase. But when it comes to reverse phase, you have a polar mobile phase and non-polar stationary phase. Correct? Stationary phase is non-polar and mobile phase is polar in reversed phase chromatography. Whereas normally you would have the mobile phase being non-polar and stationary phase being polar. Mostly you see reverse phase in hydrophobic interaction or some cases of affinity chromatography, right? So for in case of reverse, think about paper chromatography or thin layer chromatography. You had butanol, acetone, or water going over the stationary phase, right? So that is a case of normal phase or general case of chromatography. Whereas in reverse phase chromatography, you have the mobile phase being polar, more ionic or water based, and the stationary phase being non-polar, which is hydrophobic. Okay, based on the polarity, the separation is going to happen. Question 3: two proteins of molecular weights 2 into 10 power 5 and 2 into 10 power 4 were eluted out of a gel filtration column at 4 minutes and 7 minutes respectively. Determine the molecular weight of a protein which elutes out at 5 minutes from the column under the same condition. So in a gel filtration column, you're going to have medium of different pore size. Of course, the pore cutoff is going to be constant for a given column. So what is the principle? The separation principle is based on size. So larger the molecule, faster it is going to elute. Smaller molecules are going to come later. Correct? So it is going to be inversely proportional to the elution time. I'm just giving you the visuals while waiting for your answer. So let's say this is the molecular weight. And as a hint, I'm going to take log of molecular weight, and you're going to have elution time. And it's going to have a negative slope. You get what I mean? And it has an intercept here. So based on this you should be able to arrive at the formula. So let's say this is 4 minutes and this is 7 minutes. Now the scale is not very appropriate, just bear with it. This is 5, let's say this is 6. Okay, so you're having 2 into 10 power 5, and this is not in log, this is normal units, and this is 2 into 10 power 4. Again, this is in normal units. You have to convert it into uh, log and enter here. Oh, I made a mistake here. So at 7 minutes you have 2 into 10 power 4. So you can see that there is an intercept and a slope, and you have the x and y axis. So what does that mean? Y is equal to mx plus c, right? Yes or no? And since the slope is a negative trend, falling trend, you know that m is negative, correct? So this is going to be negative, and this is the intercept. So shall we write the formula? So in class it was discussed v is equal to a minus b log m, where m is the molecular weight, and this is the elution volume, correct? Are you all with me? So the same formula you can use for elution time also, correct? And I'm assuming it's to do with T naught here. So T naught is equal to a minus b log m. Have log m here, elution time given here. You have two givens, so you can solve for the variables a and b, correct? I'll wait for 1 minute so that you can work this out and tell me the answer. Any answers? Can you solve it with me now? A minus b into, let's just find out what log of 2 lakh, right? 5.3. A minus 5.3 into b, and 4 is equal to a minus log of 20,000 is 4.3. 4.3 into b. So we know that this is 5.3, this is 4.3, correct? In log terms. So now if we solve for this, so I'm going to subtract 7 minus 4 is equal to 3, a minus a is 0, 5 minus 5 plus, huh, okay, so I think I've mixed up this, right? 2 into 10, 2 lakh gave us 5.3, and yeah, 2 into 10 power 5, log of 2 into 10 power 5 gives 5.3, and 2 into 10 power 4 gives us 4.3. So plus 5.3 minus 4.3 is equal to 1, or b is equal to 3. Correct? Okay. Solving for A. 7 is equal to A minus 4.3 into 3, 12.9, or A is equal to 12 plus 7, 12.9 plus 7 is equal to 19.9. So you have solved for both constants. Now coming to the question, determine the molecular weight. So what is M of a protein which elutes out at T naught is equal to 5 minutes from the column. So T naught is equal to A minus B log M. So 5 is equal to 19.9 minus 3 log M. So bring it to the other side. 5 minus 19.9 is 14.9 divided by minus 3 would be log M is equal to 4.9667. So take antilog on both sides, solve for M, or raise it to the base of 10. So you get 92, I'm getting 92,611.87. So I'm going to round this off as 612. I hope in Daltons. So this is my answer. Are you all getting the same? Okay, it says 630, but we got 612, right? 92,611.87, or 92,612. Are you guys getting between 630 and 700? Because according to my calculation, I'm not. 14.3, 14.9 divided by 3. Okay, I had a series of 666 in my calculator. It just did with the answer. So if I did with just 9.4.967, then I'm getting M is equal to 92,682.98. So I can round that off to 683. It's just a calculation sort of error based on the decimal values. So in that case, I would get 92,683, and it still falls within the range. What about you guys? Are you all with me? Can't see any reaction here. Was that clear? So I had multiple sixes here before 7. Then I got this value. If I use just this, I'm getting 92,683. But then we are just concerned about the method of solving the problem. So just go with 2 or 3 decimals when you're doing your actual problem. So let me see what happens if I use 4.97. So it goes all the way till 93,325. So it's all to do with the decimal. 4.96 would give you 91,201, and 4.7, I mean 4.97 would be 93,320. Okay, so that's. I'm still waiting for you all to say you're okay with this. Did you all arrive at the same thing? It's fairly simple, but maybe you can try it out later. Okay, moving on to question 4. Two proteins in a mixture have a concentration of 0.25 millimoles and zero point 0.3 millimolar and have molecular weights of 2 into 10 power 5 again and 2 into 10 power 4 again. So, what is the weight, average molecular weight of this protein mixture? Let's take a minute. I hope you know how average molecular weight is determined. Summation of all concentration multiplied by molecular weight by sum of all concentrations. So here it would be C1M1 plus C2M2 divided by C1 plus C2. So I've saved you some time, and the formula is right here. Please just substitute these and tell me what the answer is. So you're getting an average molecular weight here of the whole mixture. Thank you, Natarajan. So shall we check if Natarajan is right? What is 1/4 of 2 lakhs? 50,000, right? 50,000 plus zero point 0.3 into 20,000. 3 twos are 6, and you chop off one decimal. So that is 6,000 divided by 0.55. Correct? So 56,000 by 0.55. Let's see. 56,000 divided by 0.55 is 101,818.18. Ujja has gotten 96,909. Let's see what the answer says. Okay, it's between 101,800 and 101,840. Urja, just check if you have gotten all the decimals right or any denominator errors, numerator errors. I'm just going to approximate this to 101,820 or at least 818.2. Not much of an approximation, but yeah, we fall within the range, right? So 101,880. So this is our weight, average molecular weight. Cool. So going to question 5. The standard deviation of a chromatographic peak eluting at 6 minutes is 0.33 minutes. What is the number of theoretical stages of the column? What are they asking you? Number of theoretical stages. We discussed this in last class also. Instead of height equivalent to theoretical plates, we are calling it theoretical stages here. So the question is, what is n? And eluting at 6 minutes. This is your T naught. And what are they giving you? Standard deviation. And let me know if you know the formula already, or if you want me to list it out, I can. Any answers? So what is the formula for standard deviation? So in terms of chromatography, although you might use mu and sigma in differently in statistics, here we are talking about chromatography where the base is 4 sigma, and standard deviation per se is in with respect to column chromatography that we are talking here, sigma into T naught is the standard deviation, and here they have told you that it is 0.33, and you know that T naught is 6 minutes. So what does that give you? Sigma is equal to 0.33 divided by, I'm sorry, so you can substitute here 6. So what is this? Both this will go by 3 and that will go by 11 table, right? This is 0.11 and this is 2, so 11 by 2 will be 5.5 and 1 decimal extra, correct? Let me just check with my calculator. 0.11 divided by 2, 0.055. So this is your sigma. So what is the use of finding sigma here? How do I relate this with number of plates? So in the lectures it was said sigma square is equal to 1 by n, where 1 is the number of theoretical stages. So what does that tell you? N is equal to 1 by sigma square, correct? Can you solve for this? See, it's not like some very great mathematical problem. I don't think I'm giving you silly challenges. I just want you to be awake during the class. It's okay if you have listened or if you haven't listened or if you're not very comfortable with the concepts. We're just doing this to familiarize ourselves, get more comfortable with concepts, problems, solving, everything. So it's fine. You can always reread, go through. Thank you, Natarajan. Thank you, Ulcha. So 1 by point not double five square. So I'm also getting 330.57. I'm just going to take it as 330 stages because you cannot have half a stage, and I don't have the heart to take it as a full stage. Okay, so when you're talking stages, it is always better to go with the previous whole number. Okay, so I'm going with 330 stages. All right, great. So question 6. In the previous problem, if a solute of 0.22 millimolar is injected into the column, what will be the maximum peak concentration that will be observed in micromoles? So in this problem, you have T naught, you have N, you have sigma. What are they asking you now? First, let's understand what is given. So concentration of a solute. So the feed concentration is equal to 0.22 millimoles. This is injected into the column, which means this is fed. This is feed. What will be the maximum peak concentration? So in this graph, whenever you have a Gaussian distribution, don't mind the accuracy of or the symmetry of the peaks. It's just a representation. So in the middle, you have the highest or the peak or where the concentration is the maximum. So this is what you refer to as T naught. Any other point you could just call it as the T at that particular point, correct? And the concentration corresponding to this T naught is C naught. So we are having concentration on the y-axis and elution time in x-axis. So this is the C naught and T naught in a elution profile. Now, if a solute of 0.22 millimolar is injected into the column, what will be the maximum peak concentration? So they're asking you C naught is equal to what? That will be observed in micromoles. So how do you find that? Remember this formula? So you are not using any other information from the previous problem except this, right? So substitute this and tell me the answer. This is the last numerical for the day. After that, we just have MCQs. So just give me this answer and I'll stop bugging you for values. I'll still be asking you options. Point not 483. Shall we check, Natarajan? Is equal to point 22 by 2 pi. I'm just going to use pi in my calculator. So 660 pi. So let's see, 660 into pi is 2.073. Taking root of that is 45.535. So dividing it, I'm getting 4.83 into 10 power minus 3. Exactly the same as Natarajan. Thank you, Natarajan. So let's check the answer. Oh, they've asked in micromoles, correct? So now we have started with millimoles. Oh, I've made a mistake here. So this is micro, correct? So millimoles already has a 10 power minus 3. So that 3 and this 3 together will give you 10 power minus 6, which is in micromoles. So directly I can take it as 4.83 micromoles. Yes or no? Correct? Cool. We fall within the range. So our answer is 4.83 micromoles. Alright, proceeding to question 7. Oh, there's no graph given. Can you spot the color difference? Yes, right? Evolution is taking place in this direction. So with evolution, you have a peak of B and a peak of A. Or let me simplify it better for you. Oops. What's the answer? Which is getting eluted at a higher rate. Okay, at this let's say in this time frame. Thank you, Urja. So, uh, let's take a time frame where both components are getting eluted. Of course, B is getting eluted at a higher rate. That's why it's coming out first, right? B is getting eluted faster. Yes or no? So if you argue that in this frame only B is probably having a lower molecular weight or something, even in any stage that you take, or even you cannot take after this stage and argue which of these components. But until we have a mixture or any point before this, you can say that B has a higher elution rate than A. Even here you can say that B has higher elution rate, so it got eluted before A. Correct? It's not A and B. It's not A definitely. None of the mention is a bogus option. So it is B. This is concentration, and with elution volume also you can look at this, right? Time or elution volume. Both will tell you that whichever compound comes first has a higher elution rate. I've given a broader B so that you don't confuse it with the rate of elution and the peak width. Okay. So however it is, the peak width is only going to tell you how efficient it is getting eluted or how well it is getting separated, right? How many theoretical plates you have, how much time does it have inside the column to actually concentrate into a sharp peak and all that. But the rate of uh, elution is to do with the elution volume or the time with which it comes out, correct? Good, Urja. So, question 8. Theoretical plates are used to do what? To determine what? Option A, determine the thickness of the mobile phase. Option B, determine the thickness of the stationary phase. Option C, estimate the efficiency of the column. And option D, measure the distribution of the analyte between. Thank you, Urja. Others? What about Natarajan, Saravanan? Who else there? Rahul? Answers? Okay. We had discussed this in the previous class too. So in column chromatography, we are, although it's a single column, okay, it is continuously having stationary phase as well as mobile phase passing through it. So I'm just assuming a beaded medium. Correct, Urja, you're right. uh, Whenever the mobile phase is passing through the stationary phase, you can consider each of these. See, these are you can think it as of as imaginary, but that's why we are calling them theoretical in the first place. So through scientific or methodical calculations, we are able to determine that the chromatographic column is composed of so many theoretical stages or plates, which is able to arrive at this particular separation or concentration, right? So if each of these were a stage of chromatography, so some process, some separation, some concentration is happening here, some retention of certain solutes, the allowing of you're allowing certain solutes to pass through while certain solutes are retained. So you're creating some time gap between uh, different components in a mixture. So that is creating separation. Indirectly, purification. Right? So, greater the number of stages, better is the purification, separation, or the efficiency of the column. Right? So the theoretical plates are not going to determine the thickness of the mobile phase. There's no thickness for a mobile phase. It's mostly a liquid if you're in the type of chromatography that we are mostly focusing on. And mobile phase has to be either liquid or gas. I hope this color is good enough. Right? So it is going to be liquid or gas. So definitely this is not the right option. Determine the thickness of stationary phase. So the stationary phase thickness, if you're talking about the bead diameter or thickness, then it will determine the pressure, the pore size, or the amount of surface area available to attach functional groups or ionic groups here, if it's an ion exchange resin. But theoretical plates are not used to determine the thickness of stationary phase. It's the number of stages in a chromatographic column which is going to give effective separation. Right? So estimate the efficiency column to measure the distribution of the analyte between mobile and stationary phase, not so much. Maybe your KD will do that, correct? But not theoretical plates. Right? Even the retention volume can help you a little to understand if the analyte is more likely to be in mobile phase or stationary phase or how well it is associated and etc. The theoretical plates as such is to determine the efficiency of the column and how well it can separate. So better is the higher the theoretical plates, a peak which is like this can turn into a peak that is sharper. So you're getting more concentrated peak coming in less volume or less time. Okay, so this is highly desirable, the sharpness of a peak. So it is highly compressed into a single small stage or plate. So that prevents any. So if it is like this, the next solute might have something like this, some profile like this, and it overlaps. But the more thinner or more steeper, slimmer my peak is, we are going to avoid it clashing with the next solute. If the thickness were smaller, then you won't have the overlapping here. I hope you get the concept. It's hard to draw with this device. Okay, so when n increases you get sharper peaks. Question 9. The visual output of chromatography is called, again, one happy question for you. I have already taken it out, so it's 50-50. Tell me what it is. Well, these are very silly basic questions, but I don't know if we discussed all this in lectures or this is a very simple term that you would be expected to know if you say you have gone through this course or something. So take it that way. Options A or B. Guys, take the hint from this. I have literally given you the answer here. So it's called a chromatogram. Thank you, Urja. So, product of chromatography, output of a chromatography is a chromatogram, just like thermogram, autoradiogram, anything else, angiogram, right? Last question of the day, and then you can go enjoy your puja holidays. Which of the following is not a highly specific biological interaction to be used in affinity chromatography? Remember, it's asking for not. Is it cation, anion, antigen, antibody, enzyme, substrate, receptor, ligand? Affinity. We're talking about affinity and what is not part of affinity chromatography, or which interaction, which is not a highly specific biological interaction. So, which interactions are specific here? Is antigen antibody interaction specific? Enzyme substrate reaction specific? Receptor ligand reaction specific? Cation anion specific? Thank you, Natasha. Right answer. So, all these are specific, very, very specific interactions. But cation and anions are just charge based. Although they are specific to a certain sense, these are not a highly specific biological interaction and definitely cannot be used in an affinity chromatography. These fall under ion exchange category. Correct? So option A is your right answer. With that, I don't have any more questions. If you have something to share, you can, something to ask, you can. I hope my changes got saved. Okay. Yes. If there's nothing more, we can close down the session. Thank you all for joining. Thank you for interacting. Hope to see you next week to Friday, same time. Okay then. Good night.